Bismillahirrahmanirrahim. In this lecture, I am solving problem 6.8 from the book Applied Thermodynamics by McConkey. So the statement of the problem is two vessels are connected by a pipe in which there is a wall. There are two vessels which are connected through a wall. One vessel of 0.3 cubic meter. In given data, the volume of one vessel, let they contain air. It means that V of the container, volume of the container having air is 0.3 cubic meter. Contain air at 7 bar. Pressure of the container having air is 7 bar. 7 bar mean 7 multiplied by 10 power 5 Pascal or Newton per square meter, because Pascal is equal to Newton per square meter. And temperature of the container having air is 32 degrees centigrade. 32 degrees centigrade is equal to 32 plus 273 Kelvin, which is equal to 305 Kelvin. And the other container and the other of 0.03 cubic meter contain oxygen. Volume of the container having oxygen is 0.03 cubic meter. P2 is equal to 21 bar. Pressure is equal to 21 bar, which is equal to 21 multiplied by 10 power 5 Pascal or Newton per square meter. And temperature 15 degrees centigrade. So T of the container having oxygen is equal to 15 degrees centigrade. Convert this into Kelvin, which is equal to 15 plus 273 Kelvin, which is equal to 288 Kelvin. Now the wall is open and the two gases are allowed to mix. Now the air and oxygen are mixed. Assume that the system is well lagged. Calculate. Now the wall is open and both gases are mixed. Now total volume. When wall is open, then total volume or total volume of the mixture. Mixture mean mixture of oxygen and air. So total volume of the mixture is 0.3 cubic meter plus 0.03 cubic meter, which is equal to 0.33 cubic meter. And assuming the system is well lagged mean that the system is thermally insulated, mean the process is adiabatic, no heat gain or lost by the system. Calculate the final pressure of the mixture. The partial pressure of each constituent. Number 1 required is number 1 final pressure of the mixture. Number 2 partial pressure of each constituents. Partial pressure of each constituent mean that find the partial pressure of, there are in air there are nitrogen and oxygen, so partial pressure of nitrogen. Number 2 partial pressure of oxygen. Some amount of oxygen is in air, 21%, and other part of the mixture is oxygen. There is already described that the other contains oxygen at 21 bar and 15 degrees centigrade. Number 3, at part number 3, this is part number 3. Sorry. Number 1 final temperature of the mixture. Part 1 is final temperature. This is final temperature mean final temperature of the mixture. Number 1 is temperature of the mixture, and this is number 2, and this is number 3, temperature of oxygen and temperature of partial pressure of oxygen and partial pressure of nitrogen. Number 4 is the volumetric analysis of the mixture. Number 4 is volumetric analysis. Number 5 is the value of Cp, Cv, m dot and gamma. Cp for the mixture, Cv for the mixture, gamma for the mixture, and value of R for the mixture, and value m dot molar mass, m dot for the mixture, molar mass of the mixture. Find all these values in number 5. Number 6 is the increase of entropy of the system per kilogram of mixture. Number 6 is increase in entropy. Per kilogram means specific entropy. Number 7 is find the change in internal energy in enthalpy of the mixture per kilogram. Change in internal energy, change in enthalpy, and the cooling temperature. The cooling temperature is 10 degrees. It means that in the mixture the temperature, the system is cooled up to 10 degrees centigrade. Here it is mentioned. The change in internal energy enthalpy of the mixture per kilogram if the vessel is cooled to 10 degrees centigrade. Now assume that air content consists only of oxygen and nitrogen. There are two assumptions. Number 1 assumptions. Number 1, system is well lagged. System is well lagged. Well lagged mean thermally insulated. Thermally insulated. Thermally insulated means that process is adiabatic. Adiabatic mixing. Adiabatic mixing. And number 2, second assumption is air contains only nitrogen plus oxygen. Nitrogen plus oxygen. 79% nitrogen and 21% oxygen. These are the assumptions. And there are some constant value which we will use in this problem. Some constant value which we are used in this problem. So R value, ideal gas constant for oxygen is 0.2598 kilojoule per kilogram per Kelvin. Similarly, Cp value for oxygen is 0.918 kilojoule per kilogram per Kelvin, and Cv value for oxygen is 0.659 kilojoule per kilogram per Kelvin, and the value of gamma for oxygen is 1.393. Similarly, constant value for air. For air, Cp value for air is 1.005 kilojoule per kilogram per Kelvin. Cv value for air is equal to 0.718 kilojoule per kilogram per Kelvin. Similarly, R per air is 0.287 kilojoule per kilogram per Kelvin. Gamma per air is 1.4, and the value of R per nitrogen. The value of R per nitrogen we can find is this from universal gas constant divided by molar mass of nitrogen, which is 8.3144 divided by 28, which is equal to 0.2969. Similarly, we can use the other constants, kilojoule per kilogram per Kelvin. Now we are starting the solution. So in solution, first we find the temperature of the mixture in first part. So in solution, first we find mass of the air. So as we know that PV is equal to mRT. So from this equation we know that mass of air initially in the first vessel there are mass. So pressure of air PV multiplied by volume of air divided by RT, R of air, and temperature of the first vessel contain air. So pressure of air is given to us as 7 multiplied by 10 power 5 Newton per square meter multiplied by volume of air is equal to, volume of air is given to us 0.3 cubic meter divided by R of air is 0.287 kilojoule or 287 joule. 287 joule. Joule is equal to Newton meter per kilogram per you can write this as 0.287 kilo, but when we not use kilo, then it will be 287. And temperature of air is 288 Kelvin. Now find mass, simplify this and find mass of air. Here Newton will be cancelled with Newton. Meter and meter square and meter cube will be cancelled with meter cube. Kelvin is cancelled with Kelvin. So per kilogram is kilogram. And simplify this value, which is equal to 2.399 kilogram. Similarly, mass of oxygen is pressure of oxygen multiplied by, this is basically temperature of air is not 288 but this is 305. Pressure of oxygen multiplied by volume of oxygen divided by R of oxygen and temperature of oxygen. So pressure is 21 bar, 21 multiplied by 10 power 5 Newton per square meter, and mass is 0.03, volume is 0.03 cubic meter. Cubic meter divided by the value of R per oxygen is 259.8 Newton meter per kilogram per Kelvin. This is 0.2598 but kilo. So multiply by kilo. So this will be 259.8 multiplied by 288 Kelvin. So mass of oxygen is equal to 0.8419 kilogram. Simplify this and Newton is cancelled with Newton. Per meter per square meter is cubic meter will cancel with cubic meter. Kelvin is Kelvin with Kelvin. Now total mass of the mixture is equal to mass of air plus mass of oxygen, which is equal to 2.399 kg plus 0.8419 kilogram. So total mass or mass of the mixture of oxygen and air is 3.2409 kilogram. Now in first part we have to find temperature of mixture. So as we know that MCV for the mixture we use an equation mass of air multiplied by specific volume of air multiplied MCT M1 C1 T1 CV1 plus in other vessel there is oxygen M oxygen CV of oxygen and T2 of oxygen is equal to M of air multiplied by CV of air plus M of oxygen multiplied by CV of oxygen, and to temperature of the mixture, and to temperature of the mixture. Temperature of the mixture. Now rearrange. It means that M1V1 M1CV1T1 is equal to M2CV2T2 is equal to M1CV1 plus M2CV2 and to temperature of the mixture. Means that temperature 1 means temperature of air, temperature of the vessel containing air, and T2 means temperature of the air containing oxygen. So T of air plus T of oxygen is basically temperature of the mixture. So rearrange this equation. So temperature of the mixture is equal to M of air, CV of air, T of air plus this divide by this value, divide by this value. Now putting here the values. So mass of air is 2. First I write the equation and rearrange form. M of air, CV of air, temperature of air plus M of O2, CV of oxygen, temperature of oxygen divided by M air, this CV of air plus M of oxygen, CV of oxygen. Now putting values in this equation and find T of mixture. So T of mixture is equal to mass of air is 2.399 kilogram. CV of air is basically 0.718 kilojoule per kilogram per Kelvin, and temperature of air is basically 305 Kelvin. Plus, this is plus. Mass of oxygen is 0.8419 kilogram. Multiply by CV per oxygen is 0.659 kilojoule per kilogram per Kelvin. Temperature per oxygen is 288 Kelvin. Divided by mass of air is 2.399 kilogram. CV per air is 0.718 kilojoule per kilogram per Kelvin plus mass of oxygen is 0.8419 kilogram multiplied by CV per oxygen is 0.659 kilojoule per kilogram per Kelvin. So T of mixture. Now simplify this. Multiply these three values per year. So the answer will be 525.357. 525.357. Here kilogram will be cancelled with kilogram. Kelvin will be cancelled with Kelvin. So unit will be kilojoule. Plus now multiply these three values. So answer will be 159.785 kilojoule divided by, now multiply these two values, which will be equal to 1.722 kilojoule per kilogram plus multiply this kilogram will be cancelled with kilogram, so this will be Kelvin plus multiply these value which is equal to 0.554 kilogram will be cancelled with kilogram, so this will be equal to kilojoule per Kelvin. Now further simplify this. So T of mixture, add the above two values which is equal to 685.142 kilojoule divided by add two value in denominator which will be equal to 2.276 kilojoule per Kelvin. So this kilojoule will be cancelled with kilojoule. So final answer will be in Kelvin. So T of mixture is equal to 301.02 Kelvin. Convert this into degree centigrade. So 301.02 minus 273 degree centigrade, which is equal to 28.02 degree centigrade. This is the final answer of part number 1. Now we are solving part number 2. So now pressure of mixture is equal to mass of air multiply by R of air plus mass of oxygen multiply by R of oxygen divided by total volume into temperature of the mix. This is the formula. Now put values in this formula. This is from the book. So mass of air is 2.399 kilogram. R per air is 0.287 kilojoule per kilogram per Kelvin plus mass of oxygen is 0.8419 kilogram multiplied by R per oxygen is 0.2598 kilojoule per kilogram per Kelvin and temperature of the mixture is 301.02 Kelvin divided by total volume is 0.33 cubic meter. Now simplify this value. So pressure of the mixture is equal to, here this kilogram will be cancelled with kilogram. So this 2.399 multiplied by this these two values, not 3, these two values will be equal to 0.6885 kilojoule per Kelvin and joule is equal to Newton meter, so kilonewton meter per Kelvin plus 0.8419 multiplied by 0.2598 is equal to 0.2187 and kilogram will be cancelled with kilogram. Kilojoule per Kelvin is equal to kilo Newton meter per Kelvin divided by 0.33 cubic meter and multiply by 301.02 Kelvin. So pressure of the mixture is equal to, add these two values, which is equal to 0.9072 kilonewton meter per Kelvin divided by multiply by 301.02 Kelvin and divide by 0.33 cubic meter. So instead of kilo, right here multiply by 1000. Kilo is equal to 1000. So now Kelvin will be cancelled with Kelvin, 1 meter will be cancelled with 1 meter. So pressure of the mixture is equal to 0.9072 multiplied by 1000 multiplied by 301.02 divided by 0.33 is equal to 827. Sorry, not convert this into, this is kilo and Newton per square meter is equal to Pascal, and this is 827. Now 0.9072 multiplied by 301 divided by 0.33 is 827. Now convert this into bar. So to convert into bar, divide by 100, which is equal to 827. This is 827.53 divided by 100 bar, because 1 bar is equal to 100 kilopascal. So pressure of the mixture is equal to 8.2753 bar. This is the answer of part number 2. Now we are solving part number 3. At part number 3, partial pressure of each mixture, mean partial pressure of oxygen is needed and partial pressure of nitrogen is needed. But we know that in one vessel, in first vessel, this is first vessel, in first vessel there is air, and second vessel, this is second vessel, there is oxygen. But we have to find pressure of partial pressure of oxygen and partial pressure of nitrogen. In air 21% is oxygen, and 79% is nitrogen. So here we have to find the partial pressure of 21% oxygen and 79% of oxygen. So 79% of nitrogen. Then we will add this oxygen with this oxygen, because 21% oxygen is here, and remaining oxygen is in vessel number 2, and we have to find the partial pressure of this oxygen and partial pressure of nitrogen, which is 79% in the first vessel. Okay, this is clear. Now for this we have to find the number of mole of each constituent, mean number of mole of oxygen and number of mole of nitrogen, and then mass of the each mass of oxygen and mass of nitrogen, and then we have to find the partial pressure of each constituent. So first we find partial pressure per nitrogen. Partial pressure per nitrogen is simple, but mass is needed for this. Without mass we cannot, is because mass of nitrogen is not given to us, because there is a mixture in here, there is mixture of oxygen and nitrogen. So first we find mass of nitrogen and mass of oxygen. So number of mole of air is, we know that number of mole of air is equal to basically PV divided by RT, but here this is basically universal gas. In this formula, when we use N, when we use M, then R is ideal gas constant, but when we use N number of mole, then R is universal gas constant, and there is difference between universal gas constant and R ideal gas constant. So number of mole of air is equal to PV. Now pressure of air, which is equal to pressure of air is 7 bar, means 7 multiplied by 10 power 5 Newton per square meter, and volume of air is basically 0.30 cubic meter divided by universal gas constant is 8.314 kilojoule per kilomole per Kelvin. Joule is equal to Newton meter, so kilonewton meter per kilomole per Kelvin. This is basically universal gas constant, and temperature of air is 305 Kelvin. Now this Newton is cancelled with Newton, this Kelvin is cancelled with Kelvin, and meter square and meter, this is meter cube, is cancelled with meter cube. Now N of air is equal to, simplify this, which is equal to 82.81. This kilo will be cancelled with kilo, so this is basically 82.81 mole. 82.81 mole. If we want to find it, convert this into kilomole, so divide by 1000. 82.81 divided by 1000 kilomole, which is equal to 0.08281 kilomole. This is basically kilomole. now here 21% oxygen and 79%. So number of mole of oxygen in air, not total. Number of mole of oxygen in air is 21%, means 0.21. 0.21 multiplied by 80, 0.0 0.0 0.08281, which is equal to 0.01739 0.01739 kilomole, and number of mole of nitrogen is 0.79%. It means 0.79 multiplied by 0.08281, which is equal to 0.0654 kilomole. This is in year. So total number of mole in year is 0.08281 kilomole. So 21% is oxygen and 79% is nitrogen. And number of mole of oxygen in first vessel. This is number of mole of oxygen in second vessel. In second vessel, which is equal to PV divided by RT, pressure of oxygen, PV divided by RT, R for oxygen. This is basically universal gas constant, R dash, into temperature for oxygen. So pressure of oxygen given to us is 21 bar, which is 21 multiplied by 10 power 5 Newton per square meter. Volume of oxygen is 0.0, second vessel, given to us 0.03 cubic meter, and universal gas constant is 8.3114 kilojoule. Joule means Newton meter, divided by kilomole into Kelvin, multiplied by 288 Kelvin. Volume temperature of the second vessel containing oxygen is 288 Kelvin. So number of mole of oxygen in the second vessel is basically, simplify this, which is 26.309 mole. Convert this into kilomole, which is equal to 0.026309 kilomole. Now you can calculate unit. Kilo is cancelled with kilo, Newton is cancelled with Newton. This meter and meter square is cancelled with cubic meter, and this is Kelvin will cancel with Kelvin. So this is answer will be mole, and then I convert it to into kilomole. Now total mole of oxygen. This is total mole of oxygen in the second vessel, and this is mole of oxygen in the air, in which 21% is air, 21% oxygen. So total number of mole of oxygen is equal to number of oxygen in the air plus number of mole of oxygen in the second vessel. Add these two. So number of mole of oxygen is equal to 0.01739 kilomole plus number of mole of oxygen in the second is 0.026309 kilomole. So number of mole of oxygen is equal, add these two values, which is equal to 0.0437 mole, and number of mole of nitrogen is already 0.0654 kilomole. Now we can find the mass from these values. As we know that number of mole is equal to mass divided by molar mass. So this implies that molar mass is equal to number of mole multiplied by molar mass. Cross multiply this. So mass of oxygen is equal to number of mole of oxygen multiplied by molar mass of oxygen. So mass of oxygen is equal to number of mole of oxygen is basically 0.0437 kilomole multiplied by molar mass of oxygen is 32 kilogram per kilomole. Kilomole will be cancelled with kilomole. So mass of oxygen is equal to, multiply these two values, which is equal to 1.3984 kilogram. Similarly, mass of nitrogen is equal to 1.3984 using this formula. Number of mole of nitrogen, which are 0.0654 kilogram per kilomole, multiply by molar mass of nitrogen is 28 kilogram per kilomole. This is basically formula number of mole of nitrogen, sorry, mass of nitrogen. This is basically mass of nitrogen is equal to number of mole of nitrogen multiplied by molar mass of nitrogen. So mass of nitrogen is equal to 1.8312 kilogram, and similarly total number of mole is equal to number of mole of oxygen plus number of mole of nitrogen. Add these two will already determined by us 0.0437 kilomole plus 0.0654 kilomole. So total number of mole is equal to 0.1091 kilomole. This is the total number of mole of. Now we can easily find partial pressure for nitrogen and partial pressure for oxygen. So partial pressure for nitrogen is formula is PV is equal to mRT. PV, there are two formulas. One is PV is equal to mRT. Second is PV is equal to nR dash T. When we use m mass, then this will be R, ideal gas constant. When we use number of mole, then this is universal gas constant. These two formulas are different. We can use both formula for perfect gas. So formula is mass of nitrogen multiplied by R of nitrogen multiplied by T of mixture divided by total volume of mixture. PV is equal to mRT. This equation PV is equal to mRT. So pressure of nitrogen is equal to mass of nitrogen is basically 1.8312 kilogram multiplied by R of nitrogen is 0.2969 kilojoule per kilogram per Kelvin. Joule is equal to Newton meter per kilogram per Kelvin. Temperature of the mixture is 301.02 Kelvin divided by total volume is 0.33 cubic meter. Now pressure of nitrogen is equal to, simplification is easy, multiply these three and divide by 0.33, which is equal to 495.93, and calculate the values. So this kilogram will be cancelled with kilogram, Kelvin will be cancelled with Kelvin, 1 meter is cancelled with 1 meter, so the unit is Newton per square meter, and this is kilo Newton per square meter. To convert this into bar, divide by 100, 459.93 divided by 100 bar, because 1 bar is equal to 100 kilopascal. So pressure of nitrogen is equal to 495.9, so 4.96, round the data. You can also write this 4.9593. Now pressure of oxygen is equal to, use the above formula, mRT divided by V. So mass of oxygen multiplied by R of oxygen multiplied by, this is O2, partial pressure of oxygen multiplied by temperature of oxygen divided by total volume. So pressure of oxygen is equal to, mass is 1.3984 kilogram, R per oxygen is 0.2598 kilojoule per kilogram per Kelvin. Joule is equal to Newton meter per kilogram per Kelvin, and this is 301.02 Kelvin divided by volume is 0.33 cubic meter. So partial pressure per oxygen is, simplify this now, this is easy, which is equal to 331 kilonewton per square meter. Kilogram is cancelled with kilogram. Kelvin is cancelled with Kelvin. So 1 meter is cancelled with 1 meter. This is not Kelvin, this is kilo. This Kelvin is cancelled with this Kelvin. So kilo Newton per square meter. Now convert this into bar. So divide by 100. So pressure of oxygen is equal to 331 divided by 100 bar, which is equal to 3.31 bar. This is the answer of part number 3. Now we are doing volumetric analysis. So now volumetric analysis is simple. Volumetric analysis and mole analysis are same, so we can use with the help of mole, and mole of oxygen and total mole and mole of nitrogen all are given to us. So for volumetric analysis basically volume fraction of O2 mean volume of O2 divided by V. This is basically volume fraction per O2. This is equal to mole fraction of O2, NO2 divided by N. So NO2 is equal to 0.0437 kilomole divided by total number of mole is 0.1091 kilomole. So volume fraction of O2 is equal to 0.400. Now convert this into percent, multiply and divide by 100. So multiply by 100 is 40 and divide by 100 is percent. And volume fraction per nitrogen is equal to number of mole of nitrogen divided by total number of mole, which is equal to 0.0654 kilomole divided by 0.1091 kilomole. Kilomole is cancelled with kilomole, and this is equal to 0.60. And now convert this into percent, multiply and divide by 100, which is equal to 60%. And in part number 5 we have to find Cp, Cv, M, R and gamma. So per nitrogen we know that Cv per nitrogen is this is constant value. We have to find Cv of the mixture. So Cv per nitrogen is constant value, which is equal to 0.743 kilojoule per kilogram per Kelvin. Cp per nitrogen is 1.04 kilojoule per kilogram per kilo, and Cp per oxygen is already written in the start in the constant value. So formula for Cp of mixture is equal to summation of mole fraction multiplied by Cpi. Cpi mean Cp of constituents, which is one is nitrogen and second is oxygen. So this is equal to, this is summation, so number of mole of nitrogen divided by total number, mean mole fraction of nitrogen multiplied by Cp of nitrogen plus number of mole of oxygen multiplied by Cp per oxygen. So this is equal to mole fraction is already mole fraction and volume fraction are same. This is 0.60 multiplied by 1.04 kilojoule per kilogram per Kelvin plus mole fraction of nitrogen is equal to 40%, 0.40, and Cp per oxygen is 0.919 kilojoule per kilogram per Kelvin. So Cp of the mixture is 0.99 kilojoule per kilogram per Kelvin. Similarly, we can find Cv per the mixture with the help of above formula. Cv per the mixture is number of mole of nitrogen, mole fraction of nitrogen and Cv. Here we will use Cv per nitrogen. When we find Cv, so here we will write Cv, mole fraction of oxygen multiplied by Cv per oxygen. So Cv per mixture is equal to, this is 0.60 mole fraction of nitrogen, and Cv per nitrogen is 0.743 kilojoule per kilogram per Kelvin, plus this is 0.40, and Cv per oxygen is 0.656 kilojoule per kilogram per. Simplify this. This is very simple, which is equal to 0.7082 kilojoule per kilogram per Kelvin. This is Cv per the mixture. Now we are finding R per the mixture. So R per the mixture is equal to Cp of the mixture minus Cv of the mixture. So R of the mixture, now this is easy. Cp of mixture and Cv of mixture are already known to us. So Cp of mixture value is 0.99 kilojoule per kilogram per Kelvin, and Cv per the mixture is 0.7082 kilojoule per kilogram per Kelvin. So R of the mixture is equal to, simplify this, which is equal to 0.2818 kilojoule per kilogram per Kelvin. Now gamma per the mixture is equal to ratio of specific heat constant Cp of mixture divided by Cv of mixture, which is equal to 0.99 kilojoule per kilogram per Kelvin and 0.7082 kilojoule per kilogram per. This will be cancelled, and 0.99 divided by 0.7082 is equal to 1.397. So this is gamma per the mixture. Now part number 5 is solved.